the definition of plastic deformation, it is the large movement of dislocation. So I need to apply high enough shear stress that will allow the dislocation to move or to slip inside the material. You know, it's getting more difficult if you have more dislocation, right? Because then you have to move each dislocation, right, in order to see the effect of that. Now, when you have an event, a big event, one of the biggest issue for you is the crowd management. How you can control the flow in of people and flow out. Imagine an event in a corner, we have two booths where the flow in is easier, but then the flow out will be a problem, right? Similarly here, we talk about when you have more dislocation, right? When you want to design a material, right? If you have more dislocation, then it will be very difficult to move the dislocation to allow them to move in a certain direction, right? Especially if some of the people who are attending the event, they don't obey to the whatever general direction that you have in that event. Okay. Same thing we can notice when you look inside the material. Okay. If you look inside the material, you look around the dislocation. Do you see any difference? Do you notice any difference here? Just zoom out. Do you see any difference here between these two cases? Do you hear me, Shabab?
Yes, which two?
Which two cases?
It's here. Sorry. Okay. The figure to the right, to the left here. Do you see any difference between these two cases? In the first case, the dislocation is having the two dislocation in part A, they have the same sign, right? The one to the left, you see compressive field in top of it and tensile field in the bottom, right? And the one to the right, similarly, also you got, let me just do this, okay, and then come here. Let me do this. Okay. Now you see, this is dislocation. This is a dislocation, and this is another dislocation, right? So you have the extra half plane of atom on top of this plane, right? So we have compressive field here, and they have tensile field. Do you think the material is happy about what's happening around this dislocation? Do you think the material is happy about what's happening around this dislocation?
No, because the energy is increasing.
Right, right, great. Okay.
And there is a lot of compressive forces.
Okay, you have compressive force in the top, and then you got tensile to the bottom, right? صح ولا يا شباب?
Yes.
Line here, you get compressive. Okay, great. So if this dislocation, when it starts to move as a result of the applied shear stress, imagine it had, you know, it's gonna meet another dislocation with the same sign where you have compression in the top, tensile in the bottom. What do you think the addition of these two will result in? If you add them together, what do you think that's gonna result in?
Compressive force on the top and tensile force on the bottom.
You think that will be with larger value or less value?
Larger, much larger.
Larger value, right? So then the material, do you think the material would prefer to increase more its energy or try to push these two dislocation away from each other to maintain lower energy?
To push the dislocations.
So why? Because if these two dislocations with the same sign come closer to each other, the resultant compressive field in the top of the dislocation will be higher. The tensile will be higher, right? So that means we are increasing the energy of the system in a certain region, and this is not something preferred, right? So what's going to happen if two dislocations with the same sign see each other? The result will be repulsion force between them. So they will try to push each other away from each other. طيب. Now, what do you think going to happen if they have opposite side, opposite sign? Okay.
The two dislocations will join together, forming one
Right.
line.
Right. Why do you think the material will do that?
To make the energy less of the system.
To make the energy less. Great, because the one, two. Okay. Let's come here. Zoom out a little bit. Okay. Okay. So what's happening here? If what's happening here, the one to the left in part B, the one to the left in part B will come closer to the one to the right in part B. Why? Because the one to the left, it has compression force on top of it, right? And let me just zoom out. That's going to be better, right? So the one here, this one will have a compression or compressive field in the top, tensile to the bottom. Now here it has tensile to the top, compressive to the bottom, because the extra half plane of atom here will be to the bottom because this has opposite sign. So if these two come closer to each other, the compressive field might reduce the effect of tensile field, right? Or maybe they will annihilate each other. طيب? They will annihilate each other. So they will cancel the strain field that is around the dislocation. So the result of addition of two dislocations with opposite sign is dislocation annihilation. So the extra half plane of atom that you have it here will align with the extra half plane of atom that we have it in the other dislocation. Now, if you look inside the material, one possible scenario is to have repulsion. So then what's going to happen if you want to push this dislocation to this direction, right? And this dislocation meet another dislocation with the same sign. That means this dislocation will prefer to go in this direction, right? So I mean, if you have more dislocation inside the material, and one possible scenario of the interaction is the repulsion, then there is a possibility as you increase the number of dislocation, as you need more stress in order to move the dislocation in a certain direction. This is why, if you remember, we say that if you look at the true stress strain curve, as you have after the plastic deformation, as you more plastically deform the material becomes stronger because you're increasing the density of the dislocation. And if you increase the density of the dislocation, the interaction between them, they will prevent the dislocation to move in a certain direction. So the material becomes stronger. You have to apply higher stresses from outside. Those stresses will be translated into shear stress, right, in order to move the dislocation. Okay. When we talk about density dislocation, we can compare the density of dislocation either how many dislocation we have, how many dislocation is crossing a certain cross-sectional area, or also how many of them their length per volume. So if you look at numbers, you will get surprised. Okay. So the number of the dislocation, the density can go from 10 to the power around, let's say, 10 to the power maybe 3, okay? It can go all the way to 10 to the power 10 in the material, according to the history of the material, according to what kind of stresses the material was exposed to, right? This is why I remember before when I told you, when you want to buy, say, a material, yield strength enough of, you cannot go to the table and you look at the yield strength, let's say, for aluminum. You have to know also the history of the material, because the dislocation density, according to the history of that material, might get from 10 to the power 3 all the way to 10 to the power 10, okay, per area.
Two questions دكتور.
What?
هو الآن مو احنا قلنا ان اذا يتقاربوا راح يكون بينهم repulsion.
Right.
اوكي اجل ليش في المثال اللي تحت هم ما جاء بينهم repulsion، بالعكس اتحدوا؟ هذا السؤال الأول. السؤال الثاني، هل النت effect is still the same even after when they united?
So after they got united here, you got a perfect crystal, okay? You got a perfect crystal. If here they will try to push each other away, they will go away from each other, and on average, you will have more repulsion. No more repulsion as you have more dislocation, as increasing the density of dislocation. I mean, as you increase their density, you have to apply more stresses in order to move those dislocation in a certain direction.
So the material will become stronger with more dislocations.
Right. Becomes stronger. This is why if you leave the material and you go back and then you apply the stress again, now you need higher yield strength in order to start to plastically deform the material. Why? Because during this plastic deformation, you increase the density of the dislocation. You increase their density, and if you increase their density, you need to move them. And if you need to move them, there's one possible scenario: they will try to push each other away, right, to opposite direction. So that means you need to apply higher stresses in order to initiate the plastic deformation again. And if you leave it and you apply again, similar thing, not going to happen. You're going to need higher yield strength. But one interesting thing is that in the previous figure, we say that the dislocation will move from this point all the way to the end. I mean, the dislocation line, okay, the dislocation line will move from here, all the way to outside. That movement of the dislocation line, the slip of that line will be on a certain plane. The slip of the dislocation line will be on a certain plane and to a certain direction. Because inside the material, there are many directions the dislocation can move to. And there are many planes the dislocation can slip on. And the question that we have, which plane or which direction the dislocation will slip on and will slip to, right? And to answer this question, the material will tell you, I will let that dislocation to slip in a direction and in the plane that has more closed packed or more density. So the closed packed planes and closed packed directions, because that would result in less distortion, less lattice distortion in the material, okay? That would result in less lattice distortion in the material. And what we'll do in the next lecture, we will try to get deeper into this. But just to give you a quick thing here, if you look at this plane, 111 plane, part A here. So what do you have in part A? You have plane 111. This is the closed packed plane in FCC. In that plane, this is called slip plane. There are 3 possible slip directions B, E, and C. B, or let's say AD, DF, and AF. Okay? All these directions are the family of 0, 1, 1 direction. That means in a single plane, the dislocation can slip into different direction. Those directions are called slip direction. The combination of slip plane and a slip direction is called slip system. What we will do in the next class, inshallah, we'll talk about what are those different slip systems that exist in different crystal structure, FCC, BCC, HCP, and how that will affect the ductility and the plastic deformation of the material. So I will stop here. I will see if you have any question.